So let's keep discussing this surface tension property and the different ways that we can observe it. So we were saying that there is an overpressure inside a spherical drop. There is a difference between the pressure inside and outside that is, for a spherical drop, 2 sigma over r. Right? So the pressure inside a drop will be larger for smaller drops. You agree? So if you have a very small r, you get a larger delta P. So to illustrate this, let's look at a situation with soap bubbles. Now let me just note that for soap bubbles, what we have is 2 interfaces. Right? The soap bubble is a film of water with soap. So you have air, water for a very thin layer, and then air again, right? So there's 2 interfaces. And so for the case of soap bubbles, really, we have delta P with these guys are, the inside of the soap bubble is sealed from the outside atmosphere, and delta P is going to be 4 sigma over r, because we have 2 interfaces, okay? And we consider the film of water to be very, very thin. It is, in fact, very, very thin. So what we have in this situation over here is 2 soap bubbles connected by a tube, and one is smaller than the other. And so therefore the pressure on the smaller bubble should be larger. You agree? Yes? Pressure on the smaller bubble should be larger. So what happens? Because pressure in the smaller bubble is larger than the pressure in the large bubble, there is a flow of air from the small bubble to the large bubble. And that makes the small bubble grow smaller and the large bubble grow larger. Make sense? That's right. So that's really what happens in foams and emulsions. The film here on the right is a microscope look at some foam between 2 glasses, 2 glass plates, small little glass plates that you can put under a microscope, and you have some foam, and you can see here that originally you have a lot of smaller bubbles. Over time, you have less and less smaller bubbles, and the bubbles overall get larger. That is an effect that probably you're used to seeing in your daily life. And now you understand why. The pressure inside the smaller bubbles is larger, so as soon as 2 bubbles come into contact and there's a possibility of mass transfer between them, the small bubble simply gets, gives all of its inside air to the large bubble basically and disappears. And so the small bubbles get smaller and the large bubbles get larger. Basically, foams and emulsions are dispersions of tiny bubbles. That's what a foam is. And they are systems with very large interfacial area. And so we said already that interfaces tend to minimize interfacial area. And so this is the evolution that we see here, an evolution over time to reduce the overall interfacial area. And small bubbles disappear over time while the larger ones grow in size. And this is a similar also process that you can see in emulsions. And so this is why if you have an emulsion, it's very hard to keep an emulsion stable over time. They're naturally unstable, and so you could have, if you leave something that is a mixture of oil and water, say that you could have shaken quite a bit and created an emulsion, if you leave it there for a while, they will separate, right? The bubbles, the small little bubbles of oil, all merge together, and the interfacial area evolves towards a minimum area, which in the case of two liquids would just be one interface between the two. If you had, oil and water, you probably are used to seeing that in daily life. It's no surprise. But this is the explanation. So here's a soap film, again, to try to explain this idea of tension. So if you see the soap film being formed there in that rectangular wire frame. And there's a little wire here that is free to move. And the soap film on the right was punctured. When this part on the right was punctured, the soap film on the left pulled that crossbar all the way to the other end, like an elastic. That's the tension. You can see here how the thin film of soapy water is dominated by tension, by sort of like a tension, but imagine like the balloon, right? It occurs on the skin. Okay, and there's this other one here where we have a similar situation of a soap film which is punctured, and watch it happens rather quickly. Even though it's filmed with a high-speed camera, the film immediately propagates that puncture all the way to the frame. Again, soap films are dominated by tension, which acts to reduce the surface area. Question? No? Okay. So you asked earlier about whether temperature affects surface tension, and indeed there are two ways to affect surface tension. One is changing the temperature, and generally what you will see is that surface tension decreases with increasing temperature, and the example that I have put here in this graph is water and air, where the surface tension for water goes from 73 micronewton divided by meter at 20 degrees Celsius to about 58 micronewton divided by meter at 100 degrees Celsius. So that's more or less what you would expect. Now, another way to change surface tension is to add what are called surfactants. Surfactants, the word surfactant comes from surface active agents, and basically they're special molecules that have a structure which is, the molecules have a structure which you could call like a head and tail structure. So many times you will see cartoons of surfactants that sort of have this sort of, that's the cartoon for a surfactant, the structure of its molecule that you will see. And one end is general hydrophilic, and the other end is hydrophobic, meaning that if you put these molecules on a surface of water, they will sort of arrange themselves like that. So you have sort of a bucket here of water, and imagine we're looking at the molecules. They sort of arrange themselves in this way, and they, in that way, change the surface properties. And the way they change the surface properties is by reducing the surface tension. As you add more and more surfactant, the surface tension is reduced up to a point of saturation where just the molecules start to equally fall into the bulk of the liquid in every direction, and then you don't see any additional change in surface tension. So they sort of saturate. Okay. They reduce the surface tension as you add little by little, and then it saturates. Yes?
So water, air there, does the surface tension depend on both fluids in the interface or just one?
Yes, it will depend on because if you had, say, water with oil, there would be a different property of that interface, yes. Let's see a couple of examples. In the left, let me pause it. What is going to be seen in the left is a layer of an oil type material and some little powdery material is being sprinkled on the surface just so that you can see the motion, okay? And then like a soldering little bar is approached to the surface, so it heats locally that oil. And then you see, because it heats locally, that should decrease the surface tension, and then you're going to see a motion which is due to that surface tension gradient. Okay, look at it. In the video, and then you see a soldering iron there. And there's an outward motion from the hot spot. Yes? This is what we have on the right. Ice cube being dropped. The opposite effect. So this is what's called the Marangoni effect. The gradients in temperature or a surfactant concentration generates a surface tension gradient which causes flow from regions of low to high surface tension. So recall, a liquid with a high surface tension will sort of pull more strongly than a liquid with a low surface tension. And therefore, if you have an area of high surface tension, that kind of tends to pull the liquid, and this produces a flow from low to high surface tension. Yes, the fact that you have a gradient of surface tension implies that there are some forces that are higher in one area than another, and that induces flow. Yes. The tears of wine. I mentioned this in the first lecture, and you can see this very nice visualization here of the tears of wine on the shadow. And I said to you I was going to try to explain this to you later in the course. And the explanation is the following. Alcohol has a lower surface tension than water. And so alcohol and water mixed in different concentrations will, of course, produce regions of high surface tension and other regions of low surface tension. Also, it is also true that alcohol and water evaporate at different rates. The end result is that on the film of any basically wine or any liquor is a mixture of alcohol and water, and as you have a layer of that on the glass, the alcohol will evaporate. Perhaps there's also sugar and so on, and then in these little drops you will have a varying concentration of this mixture. And this varying concentration then results in, again, a surface tension gradient. And this surface tension gradient basically will result on, well, the areas of lower concentration of alcohol will have a greater surface tension, and those areas are going to pull the liquid with more, with a higher force. And that's what you see in these tiers, the effect of that sort of flow. The surface tension gradient produces a flow, and that flow is from low to high surface tension, or from basically high, so lower concentrations of alcohol are going to be greater surface tension, and so it'll go from high concentrations of alcohol towards low, because that's low to high surface tension, right? And those effects produce these interesting little shapes on that film of alcohol-water mixture on the glass. Okay? So, we were discussing in the break with one of your classmates about the contact angle, so I think it's another concept that we need to understand. When you have the situation you were describing is not just an interface. We actually had three phases in that situation you were describing: the gas, the air, the liquid, and the solid. And so in a triple interface of that sort, you have what is called a contact angle. The contact angle is basically the angle at which the liquid vapor interface meets the solid liquid interface. Pictured here in this cartoon on the right. That's the definition, and it is determined basically by the balance between the cohesive forces within the liquid and the adhesive solids between liquid and solid. And so we can have different situations in terms of the contact angle, which I've drawn here. You could have a small contact angle and the situation of small contact angle is related to high wetting properties. You could have, an intermediate value, or you could have a high contact angle, which is a high that is theta larger than 90 degrees, which is often referred to as low wetting. And this depends on the combination of the three materials: the solid, the liquid, and the gas phase. Okay, so let me show you some examples. Well, some drops there. You can see here a sort of high wetting situation. Of course, the feather that I showed, some slides ago was a low wetting situation, and here are different possibilities. This is the same solid, but different liquids. Of course, they're all in air, so the gas phase is always, for these experiments, usually air. Not always, but most of the time it's going to be air. The substrate here is the solid material at the bottom, and we're using oil, which has a zero contact angle, and so basically the drop completely spread out, and we see nothing there. Then this particular fluorinated oil has a zero contact angle. This other type of oil has a 30 degrees, so it's a high wetting situation. Water has 90 degrees, and mercury, you see here, 180 degrees, so practically the whole drop is just sitting there like a little ball. Then you can have a situation of different substrates but the same liquid. Here you have the same volume of water, 1 cubic centimeter, that is poured onto 3 different sort of solids. And actually the volume of water was large enough that you didn't see just a small drop. It's kind of like a puddle here. But the contact angle, you can see the contact angle here in this case is 90 degrees. In this case, well, actually, because it's 90 degrees, this is the definition of the contact angle down there. This guy here is 35, and this is 140. Yes? No, the contrary, because high wetting, the logic is it is that the liquid spreads a lot. And this is the situation that we have at the top, right? With the low contact angle, so these are the same amount of volume. So we put the same little dropper with the same exact amount of water, but the top situation was able to spread much more because the contact angle is smaller. So small contact angle is high wetting. Large contact angle, think of mercury, large contact angle, very little wetting. The mercury drop will stay like a little ball, right? And the last sort of effect I want to discuss is well, no, actually I have one more, but this one is an interesting one. Contact angle hysteresis. So what happened here, and I'm going to show it again, is the following. Let me go back. So let me explain it first. So when you have, I said the contact angle is like a property of the combination of the solid, and the liquid, and the gas phase. But sometimes you could have in the solid some impurities, some dirt or something like that. And what could happen in reality is that the contact angle that you really see is not the one from your tables, from your book, that is basically a property of the totally clean, say, plexiglass with totally clean water, with so in perfect conditions. But if the water has some impurities, or say there's some dirt on the glass, then the contact angle is, as it's forming, it could sort of get stuck. It gets pinned to, say, the impurity on the glass, and so you have the contact angle, perhaps in this situation, growing a little bit beyond what it should, until it breaks and it flows. Okay, then so what you will see in this video is that situation. The contact line becomes pinned to some impurity in this material over here, and it seems like the contact angle would be growing beyond what you expect it to because of that, until it snaps out. If you look at the opposite, and you suppose you were going to, you'll see it in the movie, extract some water from the droplet, the contact line will be receding. Again, it can become pinned on that dirt that is on the glass, and the contact angle then will be less than you would expect it. So this is the situation that we will see. We have the water on a solid which is being fed with a syringe. Then initially the contact line is pinned. By, say, an impurity or dirt or anything. Impurities either in the liquid or on the surface itself. And so this makes like the introduces an apparent contact angle increase. So then you have what is called the advancing contact angle, which is the maximum contact angle that the system reaches before the flow continues. So it's the maximum angle until the drop advances, and then as the water is drawn out, oh no, my handwriting there is pretty difficult. Water is drawn out, the opposite effect happens. Your contact line becomes pinned in the opposite direction. Again. And the smallest angle before the drop contracts is called the receding contact angle. And we're going to use theta r. So let's look at the video. So we're feeding that little drop with a syringe, and the contact angle is the contact. At one point, the contact angle will seem to be increasing when it becomes pinned. Sorry, what? No, the contrary. So if the drop was just growing, the contact angle should remain the same as the drop grows. But if the contact line on the surface is actually spreading, right? Like the drop is spreading. That line, the circumference of the drop on the table, is spreading, and if it reaches some sort of obstacle, it becomes pinned, and then basically that's when the surface needs to spill over, and the contact angle increases. That's the effect that, and then going backwards, the opposite effect occurs. The drop should be just receding with a constant angle, but the line that is moving along the surface becomes trapped in some, it becomes pinned down by some sort of impurity, and that causes the drop shape to change until it snaps out. Okay? And that, in the end of this drawing, what you have is they've captured the image of the drop at the maximum contact angle while the drop was growing out, and then the minimum contact angle when the drop was receding. And they've shown a difference. And that is what's called the contact angle hysteresis. The contact angle hysteresis is basically theta A, the advancing contact angle, minus theta R. That difference in this real situation where we have impurities and so on is what we observe. Different from the ideal situation of a perfectly clean glass, perfectly clean water that will actually always reach the same contact angle that you might obtain from the tables of properties and so on. So all of these things is quite interesting, and it leads to a lot of very interesting dynamics and interesting physics going on. And it's going to help us explain one of the mysteries that we introduced at the beginning of the class. So let's apply now this a little bit to the situation of a capillary effect. So imagine that you have a liquid here. You know that a liquid will form a meniscus, so I'm going to draw, this is supposed to be a little tube inside a liquid, and you are used to, you expect that you'll have this sort of shape where we have a liquid in here, the liquid in here, and you have this angle here. So there's an angle between there, the surface, the interface, and the solid. And this is also compounded with the effect of having sometimes in a very small length scale an adhesive, having this liquid being able to climb inside a small little pipette and so on. This is called the capillary action. And this happens when the adhesive forces between the liquid and the solid are stronger than the cohesive molecular forces on the liquid itself. And you get this little climbing of the liquid inside small interstices or capillaries or tubes. So between liquid and solid, like in this area over here, are stronger than the cohesive intermolecular forces inside the liquid. In this case, the liquid can apparently climb the walls of the solid. So for this situation here, if we look at perhaps the bottom of that meniscus with respect to the surface here, we have a certain height that the liquid is able to climb because of this. And if we take just this volume of liquid and we do a free body diagram of it, it has a force here, and it also has its own weight. The weight is equal to gamma pi r squared h, where gamma is this specific weight of the liquid. And then we have vertical force due to surface tension, right? The horizontal ones cancel out. We'll just look at the vertical component. So we need to consider that angle here. Well, theta, I've drawn it there. So just the vertical component cancels the weight, and that's going to be remember, act on all of the line of contact. That line of contact is the circumference, right, looking from above, and that little tube. So it's 2 pi r, that circumference around, times the surface tension, but I'm taking just the vertical component, and so I'll multiply by cosine theta. This is the simplification we made before. Now we're considering it. This is acting actually only, the vertical surface is acting multiplied by cosine theta. So now we can apply equilibrium, balance of forces, and we get gamma pi r squared h is equal to 2 pi r sigma cosine theta, and we can solve for h, and it's equal to 2 sigma cosine theta divided by r. Let's see, do I have, yeah, 1 r left, and gamma. So again, you see that this height will be more substantial if the radius is very small, right? If we have large radius, then this height is going to be very small. We might not even see it with the naked eye. But if the r is very small, that's why if you have a little tube and you put a small tube on the water, it will climb and it will be visible. So, in the non-wetting situation, we would have that the angle is actually not like we've just drawn it before. It will be like so. Actually, I need to draw it the other. I need to not draw it for my. I need to draw it the other way because it, instead of climbing up is the other way around. So we have a negative height, if you will. So this would be the fluid. This is the non-wetting situation. So for example, in this case, H is negative. This is the case with mercury in glass. Which is negative. It'll have a different, the angle itself depends on the combination of materials. Yeah. And to end the lecture, finally, the explanation of the feeding of the bird. What really is happening here is that there's a combination, and I really will just explain it in broad terms, and I will put the paper for those of you who are interested on Blackboard so you can actually read some more details. I've just highlighted on the paper the bits that are important, just for your enjoyment. There's a combination here of the capillary action, the surface tension, and the contact angle hysteresis that we've discussed. So there's two angles, contact angles, and so the very interesting research that was done is that a group looked at the beaks of these birds as they were feeding and tried to simulate the same action by constructing a mechanical beak. And this mechanical beak they put in a experimental setup and were able to use high-speed camera to observe it. And here's the video. Is it not playing? There it goes. This is the action of the beak. It opens and closes, and the drop climbs against gravity into the mouth of the bird. And this is the picture here is the mechanical version that reproduces that effect. And they were, they wrote a paper that appeared in Science, very remarkable result. It was quite celebrated, and they were able to explain this whole mystery with just surface tension, contact angle hysteresis, and they were able to demonstrate this in experiments. And so for those of you who are interested in knowing more details, I will give you some material online. They spin. Very good question. Thank you. They spin because they generate a vortex, and this sort of grabs, it sucks out the suspended little crabs and, yes, little things, sea monkeys.